Hello everyone, welcome to the FLAC version 8, and this is the updated version, and using this FLAC I'm going to analyze the stability of slope. So this FLAC got the 4 stages: model, build, solve and plot. So using this many stages I'm going to construct, and then at last using the plot I'm going to analyze the stability of slope. So what actually the FLAC means? FLAC actually means the first Lagrangian analysis of continua, and is a computer program used in engineering to analyze and solve problems related to mechanics and engineering purposes. So to begin with the constructions, we need the data like uh, the densities, coefficients, and internal frictions. So this for these particular problems, I'm going to use the data from one of the practical done in the field, and after we will compare it with the analytic solutions. So this is the study screen. So as soon as you open the FLAC software, you will see this motor options. Under motor option, you can choose the system of units and the user interface options. So under the system of units, I will choose SI unit, and for this particular problems we have the water table, so I'm going to choose the include water table and click OK. And here we have to enter the title, so I'm going to give the title as town and the file name as town1 and click OK. So here the project name is town1 and the title is town. And now in order to construct the model, you have to go to the new and choose the model option. So from here I'm going to choose the simple form model geometry. So let's click it, and you will came to this dialog box. So here we have to enter the slope parameters. So first I'm going to enter the rise parameter, which is 10, and let's keep the run as 20, then depth of 4, and then left of 4, and then right, let's keep it as 15. And if you want to change the direction of your slope, you can click the mirror layout and apply it and click OK, and you will see the red boundaries. This is for the adjustment of boundaries. If you mistakenly enter the wrong boundary value, you can adjust it by entering numerically or by shifting it to wherever you want. But for now I don't have to edit it, so we'll click OK. And now for this particular slope we have got layers. So in order to enter the layer, I will go to build and go to layer and see here. So for this particular problems, I've got the layer division around 9.5, but I'm not sure how I can enter it accurately 9.5. So I will click approximately and go to edit, so that I can enter the value accurately. So it is more than 9.5, so I will make it to 9.5, and this also to 9.5 and click OK. And this is exactly at the 9.5, so click OK. So I've got the upper layer and lower layer, but I need to assign the materials to each layer. So in order to enter the layer, go to the material under the build and create the new material. So I will keep the class as user itself, and then the first name as upper, and under the more column I will enter the mass densities of, let's say, 1500, the weight densities of 1800, and the coefficient of 5000 Pascal, and the friction angle of 20, and click OK. And you can assign the lower metals also. So go to the create and name it as lower and give the mass density of around 18 and the weight density of around 2100, the coefficients of around 10 kilopascal or 10,000 pascal, and the friction angle of 25, and click OK. See, now I have assigned the upper and lower the values by assigning both the materials like densities, coefficients, and the internal frictions, and now click OK. And now I'm left with the addition of water tables, so I will choose this water table and plot the water table at somewhere this point at 10. This is the point what I want, and this also somewhere at the 8, this point at 3, and this point also at 3, but I'm not sure where these points are exactly at what I want, so you can hit it numerically. You see here, this is more than 10. I will choose 10, and this should be 8, so I will enter 8, and this should be 3, so I will click enter 3, and this should be also 3, and click OK. And this is the water table I want, so I will click OK. And now we'll solve this slope by choosing the coarse or mesh, Greek, or medium, or fine. So for this particular problem I will choose coarse. So by choosing coarse, and now finally we have to solve this particular boundary problems or the slope by finding the factor of safety. So under the factor of safety parameters, I will choose the friction angle and cohesion, and then click OK. And this is the programming of factor of safety. So let's wait for a few minutes. So this is the final estimate for factor of safety, which is 1.49, and click OK. So for this particular factor of safety, I will see the failure mode. So go to the plot and see, this is the failure mode. This is the failure mode of the factor of safety 1.5. And for the for the more exploration, you can go to the item in the plot, and go to the off, click off, and click plastic indicator, and see the clear picture. So this is the clear picture of where the failure occur. This reddish asterisk, it indicates the yield in shear, which is the shear failure, and at the top there is the circle which indicates the tension failure. So this is how we are going to compare the stability of slope using the FLAC software and the analytic solutions that you have done practically in the laboratory or in the field. Thank you.